The National Electrical Code, NEC, Article 240 addresses the protection of conductors. Section 240.12 discusses overcurrent protection, and Section 240.13 covers the location of overcurrent devices. Section 240.13 paragraph B deals with the location of overcurrent protection. Subparagraph 1 states readily accessible, meaning overcurrent protection shall be readily accessible. Subparagraph 2 mentions occupant access, noting overcurrent devices shall not be located where they are likely to be exposed to physical damage or where they could be inadvertently operated. Subparagraph 3 discusses panel boards, stating overcurrent devices shall be located in enclosures or behind panels that are designed to prevent physical contact with the live parts. Subparagraph 4 addresses switchboards, specifying switchboards shall be provided with overcurrent protection for the following distribution circuit conductors. Each ungrounded conductor shall have overcurrent protection. Based on these NEC requirements, it is not explicitly stated that each high-voltage panel must have an overcurrent protection device located within a certain distance or after a certain floor. However, the requirement for overcurrent protection to be readily accessible and not likely to be exposed to physical damage should be considered when determining the appropriate location of overcurrent devices for high-voltage panels. While the NEC does not provide specific requirements, industry best practices often recommend the following. Firstly, locate overcurrent devices for high-voltage panels in a central location that is easily accessible to qualified personnel. Secondly, consider installing overcurrent devices on each floor where high-voltage panels are located, even if they are part of the same circuit. This provides redundancy and facilitates fault isolation. Thirdly, ensure that overcurrent devices are properly labeled and protected from physical damage. In conclusion, while the NEC does not explicitly require overcurrent devices for high-voltage panels on each floor, industry best practices recommend installing them in a central or easily accessible location to ensure safety and ease of maintenance. The NEC guidelines emphasize the importance of readily accessible overcurrent protection to ensure safety and facilitate maintenance. While specific distances between overcurrent devices and high-voltage panels are not mandated, the code prioritizes easy access for qualified personnel and protection from physical damage or unintentional operation. Considering industry best practices further enhances the safety and reliability of electrical systems. These practices include centralizing overcurrent device locations for convenient access and installing devices on each floor with high-voltage panels to provide redundancy and simplify fault isolation. Proper labeling and physical protection of overcurrent devices are also crucial for maintaining system integrity. When implementing overcurrent protection strategies for high-voltage panels, several factors must be carefully evaluated. These factors include the specific characteristics of the electrical system, the layout of the building, and the potential risks associated with overcurrent events. Firstly, the electrical system's design should incorporate appropriate overcurrent protection devices that are properly sized and rated for the connected equipment. This involves calculating the maximum current carrying capacity of conductors and selecting circuit breakers or fuses that can effectively interrupt overcurrents without causing damage to the system. Secondly, the building layout influences the placement of overcurrent devices to ensure accessibility and minimize potential hazards. Centralized locations, such as electrical rooms or dedicated panel areas, offer convenient access for inspection, maintenance, and troubleshooting. Additionally, locating overcurrent devices away from areas prone to physical damage or unauthorized access enhances safety and reduces the risk of accidental disruptions. Thirdly, a thorough risk assessment should identify potential overcurrent scenarios and their potential consequences. This assessment helps determine the appropriate level of redundancy and fault isolation needed to protect critical equipment and prevent widespread system failures. For instance, in buildings with multiple floors, installing overcurrent devices on each floor can limit the impact of a fault to a specific area, minimizing disruptions to other parts of the building. In addition to the NEC guidelines and industry best practices, manufacturers' recommendations and local electrical codes should also be considered when implementing overcurrent protection strategies. Manufacturers provide valuable information on the proper installation, operation, and maintenance of their equipment, including recommended overcurrent protection settings. Local electrical codes may have additional requirements or interpretations that supplement the NEC, ensuring compliance with regional safety standards. Regularly scheduled inspections and maintenance are essential for ensuring the continued effectiveness of overcurrent protection systems. These activities should include visual inspections of overcurrent devices to identify any signs of damage or deterioration, as well as testing to verify their proper operation. Additionally, updating system documentation and labeling helps maintain accurate records of overcurrent device locations, ratings, and settings. The coordination of overcurrent protection devices is another critical aspect of electrical system design. Coordination involves selecting and setting overcurrent devices to ensure that the device closest to the fault interrupts the current first, minimizing the extent of the outage. This requires careful consideration of the time current characteristics of different overcurrent devices and the potential fault currents at various points in the system. Effective coordination can prevent unnecessary tripping of upstream devices and maintain power to critical loads during fault conditions. Furthermore, surge protection devices, SPDs, play an important role in protecting electrical systems from transient overvoltages caused by lightning strikes, switching surges, and other disturbances. SPD divert excess voltage to ground, preventing damage to sensitive electronic equipment and reducing the risk of fire or electrical shock. SPD should be installed at the service entrance and at downstream distribution panels to provide comprehensive surge protection. The selection of appropriate overcurrent protection devices depends on several factors, including the voltage and current ratings of the circuit, the type of load being protected, and the expected fault current levels. Circuit breakers are commonly used for overcurrent protection in residential, commercial, and industrial applications. They offer the advantage of being resettable, allowing for quick restoration of power after a fault is cleared. Fuses are another type of overcurrent protection device that provides reliable protection against overcurrents. Fuses are sacrificial devices that melt and interrupt the circuit when an overcurrent occurs. They are available in a variety of sizes and types to suit different applications. Ground fault circuit interrupters, GFCIs, are specialized overcurrent protection devices that protect against ground faults, which occur when current leaks to ground. GFCIs are required in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Arc fault circuit interrupters of size are designed to protect against arc faults, which are dangerous electrical faults that can cause fires. A size detects the unique characteristics of arc faults and interrupt the circuit before a fire can start. They are required in many residential circuits to enhance fire safety. Proper grounding is essential for electrical safety and the effective operation of overcurrent protection devices. Grounding provides a low impedance path for fault current to return to the source, allowing overcurrent devices to quickly interrupt the circuit. The grounding system should be properly designed and installed in accordance with the NEC and other applicable standards. Regular testing and maintenance of the grounding system are also important to ensure its continued effectiveness. The use of energy-efficient lighting and appliances can reduce the overall load on electrical circuits and minimize the risk of overcurrents. Energy-efficient devices consume less power and generate less heat, reducing the strain on wiring and overcurrent protection devices. Upgrading to energy-efficient lighting and appliances can also lower energy bills and reduce environmental impact. The National Electrical Manufacturers Association, NEMA, provides standards and guidelines for electrical equipment, including overcurrent protection devices. NEMA standards ensure that electrical equipment meets certain performance and safety requirements. Specifying NEMA-rated equipment can help ensure the reliability and safety of electrical systems. Continuing education and training are essential for electrical professionals to stay up to date on the latest codes, standards, and technologies related to overcurrent protection. Regular training can enhance knowledge and skills, improving the ability to design, install, and maintain safe and reliable electrical systems. Online resources, industry publications, and professional organizations offer a variety of educational opportunities for electrical professionals. In summary, effective overcurrent protection strategies involve a combination of NEC compliance, industry best practices, careful system design, and ongoing maintenance. By prioritizing safety, accessibility, and reliability, electrical professionals can ensure that overcurrent protection systems effectively protect people and property from the hazards of electrical faults. Furthermore, the integration of advanced technologies, such as smart circuit breakers and remote monitoring systems, can enhance the performance and management of overcurrent protection systems. Smart circuit breakers provide real-time information on circuit conditions, allowing for proactive identification and resolution of potential problems. Remote monitoring systems enable electrical professionals to monitor the performance of overcurrent protection devices from a central location, improving response times and reducing downtime. The implementation of a comprehensive overcurrent protection program requires a collaborative effort involving electrical engineers, contractors, inspectors, and building owners. Clear communication and coordination among these stakeholders are essential for ensuring that the program meets the specific needs of the facility and complies with all applicable codes and standards. A well-designed and maintained overcurrent protection system is a critical component of a safe and reliable electrical infrastructure. By adhering to the principles and practices outlined above, electrical professionals can minimize the risk of electrical hazards and protect people and property from the potentially devastating consequences of overcurrent events. The continuous improvement of overcurrent protection technologies and practices is essential for maintaining the safety and reliability of electrical systems in the face of evolving challenges. Ongoing research and development efforts are focused on developing more advanced overcurrent protection devices, improving coordination techniques, and enhancing the integration of overcurrent protection systems with smart grid technologies. As electrical systems become more complex and interconnected, the importance of effective overcurrent protection will only continue to grow. Electrical safety is a shared responsibility, and everyone has a role to play in preventing electrical hazards. By promoting awareness, education, and compliance with safety standards, we can create a safer environment for ourselves, our families, and our communities. This also covers the importance of having a qualified professional electrical engineer to make sure that the devices selected are compliant and safe for building operations. They would know and be able to design a complete system from high voltage to low voltage and determine the best selection for each component with proper coordination to limit the impact on all devices, electrical components, and people.